We present a study of dynamic soaring. Our team consists of Antonio Bronars, Rebecca Jiang, and Siddharth Nayak. In this work, we use trajectory optimization to generate periodic motions consistent with albatross dynamics, with essentially no energy input from the albatross. We then use LQR to improve tracking of the optimized trajectory. Albatrosses use a dynamic soaring strategy to extract propulsive energy from the horizontal wind shear layers formed a few meters above the ocean surface, and can fly for hours or even days without flapping their wings. Albatross motion is nonlinear and underactuated, making for interesting use of nonlinear trajectory optimization. We formulate the trajectory optimization as a direct collocation and consider two different sets of constraints that require two different characteristic types of albatross flight: traveling and non-traveling trajectories. Traveling trajectories are S-shaped and emit alternating turn directions, while non-traveling trajectories are O-shaped and have consistent turn directions. We optimize the trajectories by dividing a single period into n collocation points and subjecting these points to the following sets of constraints. The trajectory over a single period can be repeated to find trajectories for longer albatross flight. We approach the trajectory optimization as a constraint satisfaction problem and use a null cost. We constrain the initial altitude of the albatross to be at 0, the height of the shear layer, at t equals 0. This is because crossing the shear layer allows the albatross to gain energy, and this constraint ensures that this critical point occurs during the period. We constrain the periodicity of some of the albatross's state variables. Traveling trajectories are periodic in z, v, psi, and gamma. These state variables represent the height, albatross airspeed, relative heading, and air relative flight path angle, respectively. Non-traveling trajectories are additionally periodic in x, a horizontal position coordinate. Finally, we enforce that the albatross dynamics obey a simplified glider model commonly used in dynamic soaring literature. The results for optimizing the trajectories with a 7-second period, 7.8 meters per second wind strength, and 12-meter thick shear layer are as follows. We see looping 3-dimensional trajectories for both types of flight. Note the qualitative differences between the traveling and non-traveling trajectories, namely the sharper and alternating turn angles of the traveling trajectory versus circular non-traveling trajectories.
We experiment with modulating the period length, wind strength, and shear layer thickness for both the traveling and non-traveling trajectories. For traveling flight, increasing the period length leads to the trajectory completing more than one cycle of upward-downward motion in the allotted time, suggesting that there may be some fundamental characteristic period of the albatross flight under given wind conditions governed by energy requirements. For non-traveling trajectories, we notice a similar trend in that the albatross needs to make 2 dives during longer periods. The non-traveling trajectories look more dissimilar when varying the period because the constraints imply that the albatross cannot just double back on the original trajectory given more time. For both the traveling and non-traveling cases, there is a strictly negative correlation between the wind magnitude and maximum altitude achieved by the albatross. The trajectories with higher wind speeds also exhibit more curvature in both the traveling and non-traveling cases, traversing larger distances in the x direction, which may be explained by the fact that the higher wind speeds reduce the need to travel parallel to the wind in the y direction, and there's sufficient energy to expend more travel distance orthogonal to this direction. For the traveling trajectories, the albatross flight is composed of a larger number of smaller angle arcs as the thickness of the shear layer decreases. Thinner shear layers are correlated with less energy available for the albatross to harness, so it needs to make more tighter turns to remain in flight. For the non-traveling flight, the trajectories tend to decrease in height as the shear layer decreases in thickness. The smaller angle arc pattern is not seen for the non-traveling trajectories because of the way the dynamics of the flight type is constrained. The mechanical energy of the albatross fluctuates throughout the flight, but ends at the same value at which it started, as is implicitly constrained by the periodicity of the altitude and velocity. This indicates a balance between the energy dissipated due to drag and the energy gained through lift over the course of the flight. The direct collocation approach results in approximate satisfaction of the system dynamics due to the collocation method as well as the tolerance in the constraints during optimization. Additionally, when noise is added to perturb the system dynamics, open loop execution of the optimized control profile can result in poor tracking of the optimized trajectory. To better track the optimized trajectory, we use a finite horizon LQR formulation with the time varying linearization that is evaluated along the optimized trajectory. The LQR control attempts to regulate the error coordinates or deviation from the optimized trajectory to 0. The optimal gains can be computed offline and interpolated during simulation of the trajectory. In numerical experiments, we see better tracking of the optimized trajectory compared to open loop.